All right, PCH, welcome to our first official math pre-work lesson, trying to get us ready for our work when we come back to school for class on Monday. And so we're going to be talking a ton about functions and how to analyze them over the course of the next few weeks. And so I do want to give us a quick review on, what even is a function and how that's going to lead us into some of our pre-work that has to do with our parent functions toolkit, which you picked up from me on Friday. And so if we are looking at what we see here, right, a function very simply is a relationship or an expression involving one or more variables. And something I read somewhere else as well said it's like the idealization of how a varying quantity, so how one quantity depends on another. And we can see some examples of that here, right? I'm telling you, for this first example, or really any of these examples, that I think there's a relationship between the variable x, whatever that represents, and the variable y. And to the best of my ability, my interpretation of that relationship is formed through this function, y equals 2x minus 6. Or if we're looking over here, like the relationship between this x and this y, because g of x, f of x, and y, like those all represent y, my output. I believe the relationship between this x and this y is best represented through this function 1/2 times x minus 1 squared minus 3. Like the function is the relationship between the values. And when we're thinking about, hey, like which one depends on the other, we are saying that y, my output, depends on whatever x is. So depending on the variable x, I will plug in some number, evaluate the function. It's going to provide some output for me, which represents y. And we also call that the range of the function, whereas our x values, our inputs, also referred to as the domain. And we saw this in quite a few spaces from our algebra review practice in Delta Math. For example, when I asked you to evaluate the function here, I give you f of x. I'm saying, hey, there's some relationship between this x and y, or f of x. And so I'm saying, hey, when x is negative 8, so when x is negative 8, what is y? That means you're plugging in negative 8 in for x, evaluating, doing the math you need to come out with one single number that represents my output. Beautiful. Same thing here, right? I'm asking you for the value, evaluate f of negative 2. So that's just saying, hey, when x is negative 2, what is the y value? When x is negative 2, so I'm looking like all here, what is the y value where my function exists? And it looks like that happens up here at a y value of 8. So f of negative 2 is equal to 8. Excellent. It's going to be really, really key for us to be able to work with functions as functions like we see in this first example, or when our function is given to us as a graph, multiple representations. And we kind of saw that too in our do now from the other day, where I had a table of values that were points, right? And I asked you to, hey, plug these x values in to find the y's. Those became points on our graph to which you could also use the graph to evaluate as well. This third example was a little bit more like not difficult, but just a little bit different as far as what it was asking. It's saying, hey, what is the value of x? Like, what do I plug in for x so that it gives me a y value, because f of x equals y, f of x equals negative 1 in this case. And so if I'm looking at the graph, hey, at a y value of negative 1 this time, where is my function defined? Oh, it's defined here. And what is that x value? Oh, it's at negative 2. So when I find or plug in an x value of negative 2, it's going to give me a y value, an output of negative 1 for this function. Simple as that. And you also saw one like this, right? Again, f of x and g of x. And I know I'm hitting this hard multiple times because we need to know it. F of x represents a y value. G of x represents a y value. So I'm asking you, hey, when do the y values of my functions equal each other? And what are the x values for that too? And so if I'm looking like this is my first function, this is my second function, right? And I'm kind of scanning like, hey, here up at the top at y equals 9, right? My x values aren't the same. So that's not good. But here, like down here at 1, I find that my y values and x values are the same. Same at y equals -4 and -8, right? Like this notation is just saying, hey, what are the points of my intersection, or like points of intersection, and what are the x values that give me those points of intersection where the y values and x values are the exact same, okay? Now that's all good and well, but I think what's really, really important for us here is that we actually extend it to some real world situation, provide some context that's going to make it extra sticky for us. It's going to like help us understand it deeper. And so I want to go back to that first function that I had up there at the top, y equals 2x minus 6. And I don't just want to say, hey, like x and y are related. Like I want to actually tell you what x and y are. And so I'm telling you now that x is the number of coffees that I am selling, and y is the total profit that I get. I think that there is a relationship between how much coffee I sell and the amount of total profit I have at the very end of the day. All right, and so in order to figure that out, right, I can say, hey, if I sell 1 coffee, so when x is equal to 1, well, what is y? What is the total profit I should expect? And you could plug that in, right? Plug in 1 for x, 2 times 1 is 2, 2 minus 6 is -4. Ooh, so if I only sell 1 coffee, my profit, boom, at an x value of 1 is -4. So I'm actually losing money. Even though I sell a coffee, I'm losing money because I know that I have to like buy the materials and buy the ingredients and all the things first, and that comes out of my profit, right? When I take my expenses out as well. Let's try another one. Let's say, hey, when x is 4, if I sell 4 coffees, what is my total profit going to be? Hopefully I'm actually making profit. The money I make from selling the coffee is going to overcome the expenses that I had to incur when I first started making the coffee. And when I look at an x value of 4, yay, it looks like I make $2 whole dollars. Okay, so even though I'm not making much, hey, at least this time I'm making profit. You know what I'm saying? Now, what's really, really cool about functions is saying, hey, like if I establish this relationship between the number of coffees I sell and the total profit I can make, let's say even though I never have sold 1,000 coffees, because I'm just starting out, this is, you know, a really small business for me right now, can having this function allow me to predict the amount of total profit I can have? Absolutely, right? I can plug in 1,000 for x. 1,000 times 2 is 2,000. 2,000 minus 6 is going to give me 1,994. Boom. I'm going to have like a predicted value of this much profit. And you know, like life happens, other expenses, you know, occur, and you can incorporate that into your function as well. But very basically, right, like I've never sold 1,000 coffees, but I can predict the amount of profit I can make if I do sell that much. And so that's why functions are so, so important. And more explicitly, like being able to evaluate functions, being able to analyze them and interpret them is so key for you, no matter, like especially for this class, obviously, but like as you move on into whatever you do in the future, because it allows us to make predictions and understand the world around us on a deeper level. Okay, and so going to that sheet that you picked up from me on Friday, I have a couple of very, very basic functions that represent different relationships that an x and a y variable can have with each other. And very simply, let's start with going through this first example together. Y equals x. This, folks, is a linear function, a linear equation, because my x, my input, is just to the first power. There's nothing else going on there. It's not squared, it's not square rooted, like it's just x to the first. That is how I know it's a linear function. And that's going to be really, really key for us. I'm actually going to hit on that at the end of this video. And so when I'm thinking about a linear function, right, I don't really know what that looks like right now. We're going to pretend we don't know what it looks like. And so I'm just going to pick a couple of x values. Then I'm going to say, hey, when I plug this x value into this function, it's going to give me a y. And those are going to become points on a graph, right? We did this in the do now the other day. When I plug in an x value of -2, it tells me that literally y equals -2. So when my input is -2 for a linear function, right here, my y is also going to be negative 2. And I see that being plotted on my graph. X is negative 2, y is negative 2. Same thing, I notice, of course, for all of these, whatever the x value is, that's going to be the y. And I see this kind of pattern happening where I notice there's like a diagonal line starting in the bottom left and going to the top right. And when I actually plot the line y equals x, I see that all those points fit on it, right? But they don't stop there. I can literally plug anything in for x I want. I could plug in 1.256 for x, and what is it going to give me for y? 1.256. And I can see that. Like, that would be plotted like somewhere in here, right? 1.26 and 1.26. It is infinite, but we are only going to focus on a couple of key points. And so if we go back to our parent functions toolkit, what I'd love to see from you is say, hey, I had these x values, these inputs, plugged them in and got my outputs, plotted each of those points on my coordinate plane, and then connected those dots like I see here. All right, we're not going to go through each of these individually in a lot of detail because, like, you know the gist now. And so I'm just going to introduce each parent function by name, give you the x values I want, and then I'll give you some time to work on coming up with the y's, graphing them, and we'll check our work at the end. And so I'm just going to introduce each function to you by name, as well as provide the x values that I want you to plug in. And then I also went ahead and just threw a couple of examples down of like, hey, this is what your work should look like. I'm down in that space below. If I'm plugging in an x value of 2, showing you what that looks like for each function, and I want you to do that for every x value. And so I'm going to go through this quickly, so please feel free to pause when you need to make sure you have everything down on your sheet. And then after we're finished, we'll check all of our work together. All right, so this first function is an absolute value function. And I know that because, again, I'm paying attention to what's happening to my x. My x is inside these absolute value bars. Okay, that's how I know it's absolute value. An absolute value it just means distance from 0. So just to help you out with this one in case it's been a while, the absolute value of negative 2 is how far is negative 2 from 0 on the number line? Oh, it's just 2 spaces from negative 2. And so really what the absolute value is doing is just saying, hey, whatever's inside the absolute value, make it positive. So absolute value of negative 1, positive 1. So it's only 1 space, 1 unit from 0. You'll keep going down the line for that as well. And then again, plotting those points. The next two, a quadratic, is when my x variable is being squared. And more specifically, we'll get into some situations where we have multiple things happening. And I'm really looking for like my biggest exponent. When the biggest exponent I see is 2. That's going to kind of give me some information that's similar to a quadratic. This other one is a square root. Right? We know that a square root has this like invisible 2 there, but it's understood that that is a square root when there's no number written there. And so you don't need to write it, but that is when my x is being square rooted. Now you'll notice some of the values for x I gave you here are a little bit different from the ones we've been working with. I want you to think a little bit about why. Like, why don't I have any negative numbers for x that I'm plugging in? And why did I do 0 and 1, but I didn't include 2? Like, what would happen if I plugged in 2? Would I get a nice number, or would it be, kind of nasty? All right, only 3 more. Similar to quadratic and square root, we are also going to talk about cubic, which is when my x variable is to the 3rd power, and cube root, when I'm taking the the 3rd root, the cube root of x as well. And then lastly, we will talk about a rational function, which is when my variable is in the denominator, not in the numerator this time. Alrighty, what I want for you to do now is for each of these functions, go ahead and evaluate the function for each of the x values that I gave you and put those values into your table for y. Plot each of those points on your graph, and then we'll come back and look at what the graph should look like. I will also include the link for these Desmos graphs so that you can say, hey, like when I plot some of these points, for some of these functions, it should look like, this for absolute value at the end of the day. All right? All right, do your best. We'll come back in a few. All right, folks. The rest of this is just going to be us checking to make sure we have kind of what I have. I will include this my filled out notes on the OneNote so that if you didn't have enough time to pause and get it down, you can see it there. But the biggest things for us that we want to make sure we have right are for each parent function, we have the name, we have the correct key points, right? Because again, like for absolute value, I could plug in -4 and the absolute value would give me +4, and I see that point on my graph, but I didn't include that in my table of values because that's not going to be one of our key points. So the points that I have in my table, those are the points that we will need to be able to work with in order to graph these functions as well as graph the transformations of these functions. And so the key points here are very, very huge. And then lastly, if you're able to check with Desmos to see, hey, what does the graph look like when I actually include the entirety of the possible x values I could use here? That's what we're going to do right now as well. And so hopefully you had all your key points graphed, and then you can just look and see what I have to see, hey, what would the actual full graph look like? Because we'll talk more about this when we see each other in class. So this is absolute value. Right, kind of looks like a V, and it's going up in both directions forever. Next, we are going to talk about a quadratic, which again you've seen before. Got my different y values. And the thing about the quadratic is it's also going up and down forever to the left and right. However, it's curved. It's not two lines that are connected at a vertex, but it's two curves that are connected at a vertex. For the square root, I asked you, hey, why do you think we didn't plug in negative numbers? And hopefully you got to the understanding that, if I ask you for the square root of a -2, right, that's imaginary. We can't take the square root of a negative number, or any even root of a negative number, actually. And so that's why it doesn't show up in our table of values. It doesn't show up on our graph, because that would make this not be a function. Lastly, again, for our key points, I could have plugged in an x value of 2. And I would have gotten a nasty number, right? If I'm looking at my graph at an x value of 2, it looks like my y value is somewhere in between 1 and 2. The point exists, but it's not a nice coordinate point for us, and so it's not going to be considered one of our key points. Our key points are going to be found at x values for our parent function that are perfect squares, right? Square root of 4 is 2, 9 is 3, etc., and that's why you see those as being our key points. This function is also a curve. Okay, last couple before we finish up. A cubic, right? We can take, if we're thinking about a cube root, we can take the cube root or an odd root of a negative number, because -2 times -2 times -2 can get us a -8. And so when I cube root -8, I can get -2. So it does work for odd roots, just not for even. And so if you're taking a look at both of these graphs and tables, you'll see somewhat of a similar relationship, especially for the cube root again. I included x values that are perfect cubes. I could plug in cube root of 7, but that's not going to get me a nice coordinate point. It's going to give me some nasty decimal. And then lastly, our rational. This one didn't have as many key points because if you plugged in any number that's greater than 1, if I plugged in 6, I'd get 1/6, which is going to give me a really small decimal, and that's why you see us approaching 0. But the key with a rational is that if I plugged in 0, can I ever divide by 0? No, right? That would get me undefined. That's what UND means. And that's why I see my graph approaching an x value or a y value of 0 here from both sides, but it's never actually going to be 0. All right. You have just one question I need you to do in Delta Math. Otherwise, go ahead and review these notes before Monday and make sure you're feeling good so that we can review them, stamp them, and get ready for our transformations. Have a good one, folks.